really only two of them. You got to learn differential equations, which is kind of what calculus leads into, and you got to learn linear algebra, which is just a completely different animal than calculus, but they do a lot of the same stuff, and in many cases, like usually either one or the other is going to be a lot more efficient. But those are the two tools you use a lot. So where were we? We were working on a problem like, that's where we left off, right? Yeah, it is, because it was 2 days ago. So we were trying to make a calculus table to analyze this function, right, this polynomial. And we differentiated it. Easy derivative, we got this polynomial. Remind me, how did we know that that 4-term polynomial was going to factor by grouping? We didn't have to do anything complicated. Okay, ratio test. Ratio of the first two coefficients is equal to the ratio of the last two coefficients, and the power stepped down by the same amount in each of the two groups. And if they do that, it's guaranteed to factor by grouping, and we did that. And we got that result. Okay, so what are my zeros then? Plus or minus 4. That's it. How many times does the 4 show up as a factor? The multiplicity is 2, isn't it? Right? Okay. That might tell you something. We'll look at this problem at the end and see if we can remind me to go back, and we'll ask that question again. Could we have made a prediction about something here? Because that's when you really start getting, good at math, is when your intuition grows. As you get better intuition in math, it just gets easier, and it gets easier to learn more of it. So the more math you do, the more intuition you develop. So we can start to fill out our table. We had critical numbers, we said. Plus or minus 4, right? So -4, +4. We had zeros of the first derivative. What was our domain again? All reals. Polynomial, right? So all reals. Okay, so now what's next? Do they ask for... Okay, they don't ask for inflection points or concavity. Would we take a second derivative here? I would. I definitely would. How come? We can, and if we don't, that just means we have to use the first derivative test, right? We could, that's fine, but why not take, because it's a polynomial, the second derivative is going to be so easy to take, why not just do that? In this case, we only had 2 critical numbers, but it would be especially important. What if we had like 4 or 5 critical numbers? That's going to take a lot of time to input all those test points, right, into the first derivative test. Second derivative would be easier. It'd be more efficient. And being as it's a polynomial, it's so easy to differentiate, why not? What's our second derivative? What is it again? 3. Yeah, we're going to go from here, aren't we? We don't want it factored. We just want it as a polynomial. So 3x squared minus 8x minus 16. Okay. And so it'd be nice if we could factor that. Could we factor that real quickly? What would the magic numbers have to multiply to? -48, and add to -8. So what would they be? Yeah, -12, +4. So we could do this. We could split this into 3x squared minus 12x plus 4x minus 16, right? And so what are we going to end up getting here? See if you can just kind of do this one. You know, factoring by grouping, by the way, has to work. If we've got a quadratic trinomial and magic numbers can be found, grouping has to work. So what's the binomial going to be? Yeah, but what's the binomial going to be? When I factor out the GCF, what am I going to be left with? X minus 4. So we know we're going to get an x minus 4. What's the other factor going to be that's created by the GCFs? 3x plus 4. Yeah, everybody agree? Okay. So there's my factored form. We didn't have to do that, but it's nice to have it in factored form because then we can do the second derivative test so much more easily. We can just find the signs of the two factors. Everybody see that? And if you're thinking about this practically, I don't know, maybe the fact that you're going to get a trinomial that has a coefficient other than 1, I don't know, maybe that pushes you in the direction of just using the first derivative test. Is there a right or wrong answer? No, not really. We're just trying to be as efficient as we can. So x minus 4, 3x plus 4. So let's use our second derivative test. What's the sign of the second derivative at negative 4? Positive. So what is that? What is that? So it's got to be a minimum, doesn't it? Okay. This is kind of dorky, but there's a way you can remember this really quickly. The second derivative tells you the mood of the function. So look, that's a happy function. It's positive, right? Okay. Are you going to remember that? And then what about at positive 4? Oh, hang on. Yeah, what's happening at positive 4? Ah, we got 0. Okay, what's that mean? Okay, well, it means we don't know, right? Because look what happened. We stacked up zeros of the first derivative and second derivative at 4. So it's indeterminate, right? We don't know. It could be the 0 of the first derivative means it could be an extremum. The 0 of the second derivative means it could be an inflection point. So the second derivative test failed. That's one of those instances where it fails. It doesn't give us enough information. So what do? We go back to the first derivative, yeah.
So is that because we had 4 was used twice?
Yes, because it was a 0 of both derivatives, right? The second derivative test only works if you have a 0 of the first derivative and a non-zero number for the second derivative, okay? So then if we go back to, we're testing 4, aren't we? So if we go back to the first derivative test, we want to test a value just to the left of 4. Like what would be a convenient value to plug in for our test point? Would be the easiest point to test by far? 0, yeah. So if we plug 0 into the first derivative, we've got it factored. Doesn't even matter if we've got it factored. What's the value of the first derivative at 0?
64.
So it's positive. And another value we could pick, let's just pick something big like 10. If I plug 10 in, now we want to go to the factored form. So if I plug 10 in, what's the sign of the second derivative? Positive, right? Okay, so what's that tell us? What is this thing? It's an inflection point because it's not an extremum. It has to be one of the two. Okay, so this would have to be an inflection point, and you can even tell what kind of inflection point it is. It's got a positive first derivative, right, to the left and the right, so it's got to be doing that. Okay, so now we asked a question. Could we have predicted this? Yeah, you kind of could. How come? What about our first derivative critical numbers? There's 2 4s. So 4, think about that. And if we really think what that means, if you have a multiplicity of 2, that means that the function is going to bounce off the x-axis, right? Remember that stuff? So the derivative function is bouncing. The derivative function is not passing through the x-axis, so therefore it's not changing sign. Everybody see that? Remember that stuff? So you actually could kind of infer that right from the beginning. You would have expected that that was going to be an inflection point because it's not going to be a transition in sign of the first derivative. Do you have to do that? No, but it's kind of nice if you can see that coming, right? Does that make sense? Okay.
Before you move on,
Yeah.
can you do
asks us like where the function is, or where it's increasing and decreasing,
Okay.
it asks for like local minimum and maximum.
Yes.
Can you do that?
Yes, yeah, absolutely. So that would be when it's asking for where it's increasing and decreasing, then that's a first derivative issue only. You don't need any other part of the table. So all I need to know is where are the critical numbers and what's the sign of the first derivative surrounding those critical numbers. So if I had picked, you already know what the answer would be. If I had picked another test point to the left of -4, what would the first derivative have been? It would have been negative, right? We know that because that's a minimum. So then we know that this function is decreasing on the interval there, right? The critical numbers are what separate the intervals. And vertical asymptotes would too, but we don't have any vertical asymptotes. So from -infinity to -4, it's increasing. Okay, what about where is it, or sorry, it's decreasing, not increasing. From -4 to 4, it's increasing, and then again from, now these are open intervals though, right? So we would say it's increasing on -4 to 4, and then from 4 to infinity. We have to omit 4 because we had a zero derivative at 4. But because we have positive signs in between those critical numbers and to the right of this critical numbers, that's an increasing interval and that's an increasing interval. Okay, make sense? Okay, and what about the concavity? Which row would we use for concavity? Second derivative, and it's just the sign of the second derivative. Well, the second derivative has only got one zero, and so all we'd have to do is just plug in a value over here. We already know a test point there, right? If we plugged in a value like 10, what's the value of the second derivative going to be? It's going to be positive, isn't it, right? So it's going, hold on a second. What happened? What happened? Oh, I know, we didn't find the zeros of the second derivative. It didn't ask us to, but we could have. Where are the zeros of the second derivative? 4 and -4/3. Yeah, we would have had a zero there. And if we tested a value in between like 0, we would have gotten negative. At 10, we get positive. Does that make sense? So between the critical numbers of the second derivative, which are here and here, so this is, right? The yellow numbers in row 1 are first derivative critical numbers. The green numbers are second derivative critical numbers. On the y double prime row, this is just telling us that this function is concave up from where to where? -infinity to -4/3, right? See, now the -4 we don't care about because -4, we have a positive second derivative everywhere to the left of that critical number, right? Okay. So let's write that down. So we'd say concave up on where? It's going to be from -infinity to -4/3, and where else? 4 to infinity, right? From there to infinity, the second derivative is positive signed. And where would the concavity be down? -4/3 to 4. Yeah. Okay. Okay, make sense? Okay. All right, so next step would be dealing with some functions that involve logs. And you guys need a little practice with this because you just aren't super familiar with log functions yet. Just remember what a log function looks like, and that's very helpful. Log functions, the domain of a log function, f of x equals log x, is just all positive numbers, right? You can't input 0 because the thing is asymptotic on the negative y-axis. As x approaches 0 from the right, the log function approaches negative infinity. But it goes forever to the right. Okay, so what about a problem like that? So we're trying to figure out here inflection points and concavities, right? Okay, what's the domain of this function first? Say it again. Right, the natural log, you can only input positive numbers, right? Okay, but now think about this. What's the expression that's inputting numbers into the log function? Because there's really a couple layers to this function, right? See, the log doesn't know where the numbers come from. You're just feeding it numbers. Where do they come from? They come from here. They come from that expression. The output of 3x squared plus 1 is what's feeding numbers to the log function, because you have a log of a polynomial. You have two layers here, right? So really, what has to be true is that everything in the blue bubble, as far as the log is concerned, just has to be positive. So that's the domain. That's the domain of the log function right there. It's every place where 3x squared plus 1 is greater than 0. Okay, well, let's solve for x and see what that is. What would I do to solve for x? Subtract 1 and then, okay, so that's every place where x squared is going to be greater than negative 1/3. Well, where's that? For what real numbers is x squared greater than negative 1/3? All of them, right? Right? Because the square of a real number is non-zero, is non-negative. It's either 0 or positive, right? So that's all reals. Does that make sense? Again, the way you get there is you have to look at this in pieces. You have to say, okay, well, whatever is feeding the log function, whatever the argument of the log function, that has to be positive, so you just set up that inequality and solve it. If we had had a different inequality, what if the argument of the log had been something like 3x minus 2? If that had to be greater than 0, then we would have had a definite domain. X would have had to have been greater than 2/3. That would have been our domain. Okay? Oops. That's what I want. Okay, does this thing have symmetry? What do you think? Does it have symmetry? It does. It does. It has even symmetry. And think why it is. Think about the test for even symmetry. The test for even symmetry is this. F of negative x equals f of x. Okay, you can prove this to yourself really quickly. If I plug in negative x in place of x, does that change anything? What is the quantity negative x squared? X squared. So inputting a negative x gives us exactly the same function we started with, so you can see right away that this is even symmetry, right? Okay? So that helps. That means we really, when we're working in our table, what domain would we really have to do? I mean, we really don't have to create our table everywhere. We can just create our table from where? 0 to infinity, and then just reflect it if we want to, right? Okay, so now we need some derivatives. What's f prime of x by the chain rule? What's the derivative of log u? U prime over u. So I'm going to get u prime, which is what? 6x over 3x squared plus 1. Okay? So it doesn't ask for this. It doesn't ask us for extrema, but let's find them anyway. So where are our critical numbers, if any? 0. Any others? Yeah, where would the bottom be 0? Is it ever 0?
Oh, no.
It's never 0, right? So because the denominator is nowhere 0, that means there are no places where the derivative is undefined. The only critical number we get would be 0, which is the 0 of the top, right? So on our table, we can go ahead and do that. We'll put in 0 gives us a 0 first derivative, okay? Second derivative. So how about our second derivative? Go. Low d high minus high d low. So low is 3x squared plus 1 times d high is 6, right? Minus high. What's d low? 6x. So I could just make that 6x squared, right? All over 3x plus 1 squared, right? And so if I distribute the 6, I'm going to get 18x squared plus 6 minus 36x squared. So that's just 6 minus 18x squared. Everybody agree?
Yeah.
Right? 18x squared minus 36x squared is negative 18x squared. On the bottom, we already know what that is. 3x squared plus 1 quantity squared. So we could factor out a 6. Times 1 minus 3x squared. Okay, so what about the second derivative? Any place where it's undefined? Thumbs up or down? Right. Thumbs down, right. How come?
There's no zeros in the denominator.
Yeah, no zeros of the denominator. Okay. How about the numerator? Any place where the second derivative is 0? It's going to be where that factor is 0, right?
Yeah.
So isn't that just where x squared equals 1/3?
Yes.
Agreed? Okay. So what's x going to equal then? Plus or minus square root of that, right? Yeah. So x equals plus or minus square root of 1/3. If we want to rationalize that, just square root of plus or minus square root of 3 over 3. But you could just make it 1 over square root of 3, doesn't matter. So those are our two critical numbers for the second derivative. And we kind of knew it was going to have that symmetry anyway, right? We knew that whatever shows up on the right side of 0, there better be a mirror image on the left side. Right? Okay, so what do we do here? Yeah, so what do we want? Tell me what we want to do. For sine of what at 0? Second derivative. Okay, so let's do that. If we go back to this page, what is f double prime of 0? Positive or negative? Positive, right? Okay, so that tells us what? It's happy. Okay, we've got a relative min. Okay, what's the only other thing we need to do here if we want to know concavities and points of inflection?
Left of this and the right of the zeros of the.
Good, we need some outside test points, don't we? Say it again. Yeah, you could. You're right. So we could just do something like 10. And we know we're going to get mirror images over here, right? So now do you get well, I'll ask you that question in a second. So if we plug 10 into the second derivative, what's the sign going to be? Positive or negative? Negative. And if I plug negative 10 in, I'd also get negative, wouldn't I? Because the x's are all squared, right? So it's insensitive to the sign of x. So what does that tell us then? What's that?
Inflection point.
Right? What does this thing have to look like then? What is the value of the function at 0, by the way?
Looks like
What's f of 0?
Ln of 1.
Log of 1, which is what? 0. So we know this thing goes through the point 0, 0. We know it has a minimum. If we get a point, if we go out here to square root of 3 over 3, which is a pretty small number, right? What's it going to do? It's going to do that. Has to do the same thing on this side. So that's our picture, right? Now, what would the first derivative, the sign of the first derivative be to the left of 0? Negative. What would it be to the right? Okay, so you got to be careful with these symmetries. Does symmetry mean that the derivatives are going to be symmetrical? No, it doesn't. It means the function is going to be symmetrical or the second derivative is going to be symmetrical, but not the derivatives, right? To have a symmetrical function, you're going to have a decreasing function on one side and increasing on the other, or vice versa, right? So those are going to be opposites. Is that a big deal? No, but you just got to be careful, right? You just don't automatically fill in and say that's going to be a plus, because it's not that simple, right? The function is symmetrical. Doesn't mean all derivatives are symmetrical. Okay, make sense? Okay. Did I have a picture of that? I don't know if I did. Oh yeah, there it is. Okay, so just what we said it was, right? Okay, maybe one more before you disappear for the weekend. So how about this one? What's the domain of this function? What's the domain of an exponential function? No, all reals. Right? What's an exponential function look like? That's supposed to be asymptotic, right? So that's y equals e to the x, right? Goes forever to the left and forever to the right. Okay, so that's got an infinite domain. That's got an infinite domain. So we're fine, right? Domain's all reals. No place we'd have any problems. How about symmetry? Well, you just got to check what would happen if I plugged negative x in. That's all you have to do, right? If I want to check for symmetry. What is f of negative x? Well, the first part's still just going to be x squared, the first factor, right? Okay, but I'm going to get e to the positive 2x now, aren't I? So it's neither then, right? Because if f of negative x equaled the original function f of x, it would have been even symmetry. If it equaled the opposite of the original function, which would have been what? Negative x squared e to the negative 2x minus 5, then it would have been odd symmetry. But it's neither one of those. So there's no symmetry. Okay, so now what? First derivative. Yep. Thought you were going to at some point get a little break on the derivatives. No such luck. What's f prime of x?
product rule.
Product rule. Yeah, so what is that? This is this is kind of dumb. This is so nitpicky, but I would choose to differentiate the exponential first, so you get bigger powers of x in the first terms and smaller power. Does it matter? No, not really. But if we kept the x squared and we differentiated e to the minus 2x, what's the derivative of e to the minus 2x? What's the derivative of e to the u? E to the u, u prime. So what's u prime? Negative 2. Okay, so we're going to get a, oops. Negative 2 e to the negative 2x. There's my derivative of the second factor, right? Derivative of 5 is, by the way, 0, so we don't have to worry about that. Then we get the other part of the product rule, which is going to be e to the negative 2x times the derivative of x squared, which is 2x. Okay, make sense? So let's factor that. What could I factor out? I could take out a 2x e to the negative 2x. And I'm going to take out a negative 2x e to the x. And what's left behind if we do that? Yeah. Right? So if I write that as a fraction, we're going to get x minus, I'm going to get 2x times the quantity x minus 1, and on the bottom I've got an e to the 2x, right? Okay, so there's f prime. So we need to find our critical numbers. Where are the zeros of the first derivative? 0 and 1, right? Where is the first derivative undefined, if anywhere? Can't, right? Remember, exponential functions, remember what their graphs look like. The range of an exponential function is all positive values, right? All positive numbers. It never gets to 0. It's asymptotic. So there are no places where the denominator is 0. So we only get critical numbers of the 0 variety at 0 and 1. Now, I think I have a table for this, don't I? No, I don't. Okay, we need a table. Okay, let's take this question at face value. They only want relative extrema. So do we want to take a second derivative? No, probably not. That's a little too hard a derivative to take, too much time. So we'll just do the first derivative test. And where would we pick values? Negative 1 would work, yeah. One half. And 2, that works. So what's the sign of the first derivative at negative 1? That factor is negative times over. What's the output of the exponential function is always positive. So that gives me positive total. How about at 1/2? Positive times negative over positive, so it's negative. And at 2? Positive times positive over positive, so we got it. What is this thing? Yeah. So it's going to look like peak, and then this one's going to be a valley, and that's it, right? Okay? Make sense? Okay? So would it be useful to know concavities, though? It might be, right? Because you don't really know what's going on here. You don't really know, is this thing going down or is it doing that? Right? So if you really wanted to sketch this thing, that's not what was asked here, but that's what's going to be asked in the next section.
Could it go down?
What do you mean?
Could it, you can't go
Well, no, I mean it could just go down forever, right?
I thought it's an exponential.
Let's see. What was our original function? Oh, here it was. So yeah, that one really couldn't go down, could it? No, you're right. So you could kind of infer that. Yep.